Lecture 39, The Kinematics of Faulting. Earthquake deformation tells us a lot about the displacement of faults. The red star in the figure is the epicenter of the magnitude 7.3 Bora Peak, Idaho earthquake, in 1983. The red line is the surface rupture of the earthquake. The blue dots are land stations where changes in elevation produced by the earthquake were measured. The contours are the modeled uplift and subsidence produced by the earthquake, assuming the fault is an elastic dislocation, dipping 47 degrees to the southwest, and in the area shown by the red dashed rectangle. The dashed contours are uplift, and the continuous contours are subsidence. The footwall block exhibits uplift, with a maximum of about 20 centimeters near the fault, and decreasing to 0 to the northeast. The hanging wall block exhibits subsidence with a maximum of 1.2 meters near the fault and decreasing to 0 to the southwest. The earthquake-related vertical displacement along the southwest-northeast green line looks like the upper figure. The dots are the land stations, and the curve is the modeled displacement. Notice that the model fits the data quite well. The middle figure is a cross-section showing the modeled fault, the hypocenter of the Bora Peak earthquake as a beach ball diagram, and aftershocks as circles. Notice that the modeled fault is consistent with the distribution of aftershocks. The lower figure is a geological section across the Bora Peak fault. Notice that the fault, hanging wall and footwall blocks, resemble the two figures above. There are footwall uplift and hanging wall subsidence. However, the geological uplift and subsidence is 3 to 4 orders of magnitude larger than those of the earthquake. Are these structures as we see them today, the result of many earthquakes, as the Bora Peak earthquake, over a period of hundreds of thousands to millions of years? This is an ongoing topic of research in structural geology. In outcrop but especially on seismic data, faults display a systematic variation of heave along strike. Single faults often show heaves that increase in width from a resolved fault tip, A, to a maximum of the fault center, B, and then decreasing again towards the other fault tip, C. The systematic variation in heave on one horizon is also present on all horizons offset by the fault. A systematic variation in offset is also evident in vertical seismic sections. Single faults often show offsets that increase in size from a resolved upper fault tip, A, to a maximum, B, and then decreasing again towards the lower fault tip, C. The example is of a small normal fault. In most cases, the lower part of the fault is not imaged on seismic. For very large faults, only part of the fault may be imaged. Numerous outcrop and seismic data observations have shown that fault surfaces are approximately elliptical, usually longer than they are tall. Displacement is maximum near the center and diminishes in a systematic manner outwards in all directions to the edge of the fault. The fault tip line is the contour of zero displacement. Abrupt changes in fault displacement point to areas in the interpretation that need to be checked. The left figure shows fault polygons derived from 3 horizons. Note how the fault polygons gradually change in separation along strike. The right figure shows throw on the fault surface derived from the fault polygons. Red is high and blue is low throw. Throw varies in a smooth fashion over the fault surface. This is a fault plane profile of a normal fault from the Gulf Coast, contoured by throw. Note the tight bullseye contour pattern. Local bullseye contour patterns of very low throw relate to poor interpretation of the red and green horizons. The horizons in this region should be reinterpreted. Faults aren't isolated but they link. As a fault dies out, it usually transfers its displacement to another fault. Displacement transfer between faults is an important process in both map and cross-section. This figure shows the displacement transfer geometries on normal faults in map view. Faults that transfer displacement but do not intersect are termed soft-linked, and are separated by a continuous bed segment. Faults that intersect are said to be hard-linked, and join along a branch line. Synthetic faults dip in the same direction. Conjugate faults dip in opposite direction, and they are divergent if they dip away from each other, or convergent if they dip towards each other. The amount of fault overlap can vary from no overlap to collateral. This figure shows displacement transfer geometries on normal faults in cross-section. Bends or overlaps that trend oblique to the slip direction are either restraining or releasing, depending on their overlap direction relative to the slip direction. This is illustrated by the displacement vectors. In releasing bends, the displacement vectors point away from each other. In restraining bends, the displacement vectors point towards each other. Soft links may evolve into hard links as displacement increases, and the faults grow longer. Faults may propagate in their own plane or curve to intersect, as shown in this figure. In general, a wide spacing between the propagating faults favors overlap, and a small spacing favors linkage. A drying sand bank at the beach is a nice example. The red dots are the fault tips. Initially, there is no overlap between the faults, and they have separate displacement profiles along strike. Later, the faults propagate and overlap. The displacement profiles of the faults merge, and the zone of fault interaction is marked by a displacement minima, T2. With more fault propagation and overlap, a relay ramp structure develops. The faults are still soft-linked. More fault displacement and propagation results in breaching of the relay ramp. At this point, the faults are almost hard-linked. The displacement profile does not indicate two faults, but one long fault. With more displacement and propagation, the ramp is completely breached, and the faults are hard-linked to form a single fault. This is clear in the displacement profile. A fault bend on map view marks the linkage area. Fault bends are common on seismic data at the scale of kilometers, as shown by the figure to the left, which displays the base Cretaceous unconformity, or BCU, in the North Sea. The dashed white lines are faults. The figure to the right shows fault bends on a kilometer size, basin bounding, normal fault system, the Wasatch Fault Zone, near Salt Lake City in Utah. The different fault segments are separated by the fault bends. The yellow and black model is a centimeter-scale gypsum model of extension and normal faulting, which resembles these two examples. As we saw before, fault linkage can be indicated by the throw distribution. The throw of the fault in the middle of the map shows two throw maxima, and one low throw area in between. This region indicates linkage of two faults. This figure shows the displacement transfer at a relay ramp, where the faults are soft-linked. The arrows indicate the amount of dip separation on the faults. Outside the ramp, the fault throw is 600 units. Across the ramp, the sum of the throws of the two faults must be equal to 600 units. In other words, fault displacement is conserved along the ramp. Here is one example from seismic data. The relay ramp structure is bounded by faults 1 and 6. The throw profile illustrates the way displacement is transferred along the relay structure. The decrease in throw on fault 1 towards the west, which is the yellow line, coincides with an increase in throw on fault 6, which is the red line. The dashed black line is the sum of the throw on both faults. This figure shows the displacement transfer at the intersection of two faults, where the faults are hard-linked. The blue arrows indicate the slip vector addition at the branch line. The dip slip of fault C is equal to the sum of the dip slips of faults A and B. The red arrows show the same but for fault throw. Fault C has throw of 700 units. At the branch line, fault A has throw of 300 units, and fault B of 400 units. The sum of the throws of these faults is equal to the throw of fault C. Fault slip is conserved at the branch line. This is one seismic example. The fault plane is color-coded by throw. Note the abrupt drop in throw across the branch line, as part of the displacement is transferred to a splay fault on the hanging wall side. Checking the conservation of slip at fault intersections is a good way to evaluate the correctness of structure maps. In Figure A, imagine a circular clock around the fault intersection. Then, from 12 o'clock, proceed clockwise around the intersection, and record the vertical separation as denoted from contours projected across the faults. Assign a positive value to the vertical separation if the path across the fault is from the footwall to the hanging wall block. Conversely, assign a negative value if the path across the fault is from the hanging wall to the footwall block. Beginning at the 12 o'clock position, Fault 1 has a vertical separation of 400 feet, Fault 2 has a vertical separation of -150 feet, and Fault 3 has a vertical separation of -250 feet. The sum of these three values is 0. The intersection is consistent. Figures B and C also illustrate this method. In B, beginning at the 12 o'clock position, the first fault has a vertical separation of 1,200 feet, the second fault has -400 feet, and the third fault has -800 feet. So the sum is 0. In C, the first fault has a vertical separation of -200 feet, the second fault has 300 feet, the third fault has 200 feet, and the fourth fault has -300 feet. Again, the sum equals 0. Notice that although vertical separation and fault gap are different, they are somewhat correlated. At fault intersections, an increase of vertical separation corresponds to an increase in gap, and vice versa. So the gap should also change at fault intersections. To learn more about this, read Chapter 9 of Fossen, and do his e-learning module on faults. And answer these questions.